Hi, these are the solutions to the homework at the end of lesson 12. The first question is about a diffraction grating resolving light of wavelength 400 nanometer, which illuminates 100 slits on a diffraction grating. Using the resolvence of diffraction grating formula, substitution gives 2 nanometers for the answer, so answer is B. Question number 2 is about a single slit diffraction pattern. D would be the width of the slit, and substitution into that ratio, we can find the half width of the central bright in terms of the other quantities. Question wants the width of central max, so it's going to be twice that ratio. Answer is A. Question number 3 gives us two sources of finite width. This is telling us that they're not point sources, so we cannot ignore their diffraction effects, which means the pattern should be as shown in D. Question number 4 is about resolvence of a diffraction grating. We are given that there are 600 lines per millimeter and the beam is 2 centimeters wide, which is 20 millimeters. That gives us the number of lines illuminated. We have a light going through 12,000 lines. Substitution into the resolvence of diffraction grating formula, we can find that 0.026 nanometers difference of wavelengths can be resolved with this diffraction grating. Question 5, we have monochromatic light incident on 4 thin parallel rectangular slits. So we are looking at a multiple slit interference case. And we're also given the graph where intensity is plotted against the angle from the center. We're also given in part A that IO is the intensity of the light in the middle of the screen from one slit. And we know that there are 4, which means first we need to say that at 0 degrees, constructive interference due to the 4 slits forms. That gives the total amplitude 4A, and intensity is proportional to square of amplitude, where intensity of one slit is IO. That means when amplitude becomes 4 times larger, intensity becomes 16 times as large. 5BI is asking for an estimation of wavelength given that the width of each slit is 1 micrometer. That means 1 times 10 to the power of 6 meters as B. Now we're going to use the envelope of single slit given on the graph to look at the single slit intensity minimum. We've looked for the angle where the envelope hits 0. I read that as 0.43, but an acceptable range is given as between values of 0.41 and 0.45. If you say 0.4, that would not be right because the divisions are given very clearly, so you need to be careful about your readings in such questions. Substitution into the single slit diffraction formula gives 430 nanometers. In BII, we are required to determine the separation of 2 consecutive slits. So now we're looking for the distance between 2 neighboring slits. For this, we're going to use that formula where n equals 1. We read from the graph that theta is 0.125 radians. For this reading, we should look for the angle that corresponds to the first maximum. You should ignore the little 2 mini peaks between the central max and the first max. You don't need to consider those ones. You look for the first obvious max after the central one. So that angle is 0.125 according to the scale. Lambda we found to be 430 nanometer from the previous question. Substitution gives 3.4 times 10 to the power of 6 meters. Big warning here, you must put your calculator in radians because this angle is in radians. You might as well switch it to degrees and calculate, but it won't be worth your effort. Increasing the number of slits. We know that this causes the maxima to become more narrow and more intense. In part CII, we have a diffraction grating, which is used to resolve the 2 lines with these given wavelengths. We're looking at the second order, and we want to know the minimum number of slits in the grating that will enable the two lines to be resolved. So we're looking for n, the number of lines that are illuminated to make this happen. We are going to use for wavelength the average of the given range. You can choose to use either of these values for the wavelength in the formula. M is 2 as given, and this is the difference of the two wavelengths that is given. It solves to calculate 494, which would roughly be 500 lines illuminated. Question number 6 gives an intensity pattern formed from two slits of equal width. Part A asks us if the source is incident on many slits of the same width, what would happen to the intensity distribution diagram? Your answer should show maxima at the same locations, and they should be narrower and more intense. Part B asks for the calculation of the angle between the central maximum and the first order principal maximum formed by the grating. So we're going to use the diffraction grating formula. Wavelength is given and the slit spacing is also given. Looking at the first order, n equals 1, we calculate the angle to be 21 degrees. If your calculator was set to radians, you would calculate this angle in radians. That would not be wrong as long as you express it correctly. Question number 7 gives us light of wavelength 590 nanometer is incident on a diffraction grating as shown. The grating has 6 times 10 to the power of 5 lines per millimeter. So the first thing I want to do is to find the separation of neighboring slits, which would be 1 over that number per meter. So we have this as D in meters. We want to find n this time, and the n that we can observe with these conditions. To find how many maxima we can observe on each side, we have to look at how many degrees we have available. So I'm going to use maximum angle of 90 degrees in my formula and find n that would fit within my view in that 90 degrees. Now substitution into the formula gives the maximum n that can be observed in 90 degrees. It calculates to 2.82. I don't have the space to see the third max. That means I take the integer of whatever I found in this calculation. I can only see the first two. 2.82 fits would mean that I can see the 2 and I don't have space to see the third. So maximum 2 observed in 90 degrees. But that's not the answer, because that means I can observe 2 on one side, 2 on the other side, and I cannot forget about the central maximum, which means the answer is 5. Part B of question 7 asks for the observable difference between a first order and a second order maximum. Since the second order is at a wider angle from the center, it will be less intense and wider compared to the first order spectrum.